All right, welcome to 6.02. Today we're going to continue our work with radians. So a little bit of this will be partially some review from Friday, some similar concepts, and then we'll kind of continue it on and branch forward into a full-fledged understanding of radians. All right, so let's just get a quick refresher from what we discovered on Friday, and this was really all your guys doing. Did an excellent job of graphing the height of a Ferris wheel cart over time. And you just imagine, if you start out here, and then 15 seconds later, maybe 30 seconds later, you've gone all the way to the top. And if you think about that graph, what is that going to look like? Well, here you are rising up to the top, and you've reached the top. There you are. And then what is going to happen? Well, you're going to come back down, and you're going to reach the same points you did on the way down, right? So on the way up, you were here at one point, and on the way down, you'll be at that same height again, right? If you think about right there, right there. And eventually, you'll get all the way back down to the bottom, and that's right there. And there you've gone one full cycle around your Ferris wheel, and you'll be back at the start. And hopefully you have gone to a good Ferris wheel, and they continue around, and they'll take you around one or two more times, and so you'll do this same path again. And I'm sure you'll enjoy it, but it will still be the same exact path that you took the past time. You're going to follow through all of the heights again and again. And so our question was, what type of function can we use, can we create to represent this function? And long story short, what we came up with is that we were following the points around a circle, right? This Ferris wheel is following the points around a circle. And if we could write a function to tell us the coordinates of the points around a circle, we'd have a function which would repeat itself, right? Because if you continue traveling around a circle, then you're going to get points that repeat itself. For example, this point, we'll go all the way around, we'll come back again, and you'll see that point again, right? And so our goal is very simple. Our goal is to write a function to tell us the x and y coordinate points of a point on a circle. So, if I had some point, any point on a circle, it has an x and a y coordinate. And our goal is going to be to find a function, or to create a function which will tell us the x and y coordinates of this circle. So really our goal is to write a function to find those values, because once we do, we'll have a function that will repeat itself over time, and will continue to repeat itself over and over again. Obviously, if you continue going around a circle, it'll continue repeating itself. So the first thing that we've got to do, we have to think about how is it that we will move around the circle, right? How will we talk about different points on the circle? And this brought us to a little talk about degrees. And what we realize is, degrees are just a totally arbitrary thing, right? 360 degrees being a full turn is just a totally made up number. It could be 100, it could be 1,000. The reason that we picked 360 has nothing to do with the math behind a circle. And so we need to come up with a better way of describing the angles that we are turning. And so this leads us to radians. All right, so imagine we have a circle here. Here's your radius. Let's just give it a random length r, right? So it doesn't necessarily have to be any value. It can be anything. And consider the angle that you've turned to travel one radius length around the circle. So this arc length here is what we call it, because it's an arc, is the same as one radius length. And so that will be an angle of 1 radian. And so this here, that angle would be 1 radian. All right, and we kept traveling around the circle, right? And we decided, okay, here's about 2 radius lengths, and here's about 3 radius lengths. And ironically, a little more than 3 radius lengths is halfway around the circle. And we kept going, and here was 4 radius lengths, and 5 radius lengths, and 6 radius lengths, and ironically we found that it takes about a little more over than 6 radius lengths to make it all the way around the circle. And that shouldn't be surprising at all, because if you think about the circumference of a circle, it is 2 pi r. And 2 pi r, being the distance around the circle, tells us that you need 2 times pi radius lengths to make it all the way around the circle, right? That's what is the distance around a circle. And so this tells you that you're going to need 2 pi radius lengths. Well, what is pi? Pi is about 3.14, and so that's when you multiply by 2, that's a little more than 6, and so it should make perfect sense that to go all the way around the circle, will take a little more than 6 radius lengths. And so what we can do is we can now say that any angle, it can be described in terms of radians, meaning any angle, given the number of radians, that's the angle that it takes to go that distance around the circle. So this is going to be our new way of describing angles here. One point that we need to make, which is going to lead us to a discussion of something that is very important, is that this is going to work for any size circle, right? And this might not seem intuitive at first, but let's consider a bigger circle than this here. Okay, here's this bigger circle, and think about what it will take to go 1 radius length. Well, notice that it will be the same amount around the circle to go 1 radius length as it were to go around 1 radius length during on the smaller circle. And this should make sense. Why? Because as my circles get bigger, the radius length gets bigger. And it doesn't matter the size of your circle, you always use, 2 pi r is always going to tell you the circumference around a circle. It doesn't matter the radius length. And so no matter the circle size, you're always going to need 2 pi radius lengths to go all the way around. And so 1 radian will be the same proportion around a circle for any size circle, right? And so that's very key, right? It'll always take the same number of radius lengths to go around a circle. And so this is very key. And this allows us to think about the angles, looking at angles, and help us to travel around a circle in a way that is mathematically sound, right? Because now we have something that is based on the actual mathematical construct of a circle. And so I can say, show me an angle of 2 radians. And what you'd want to do is travel 2 radius lengths around the circle, and there's going to be, this is the angle that is 2 radians. So now we want to think about what might be a circle that will allow us to think about radians most clearly. Since it doesn't matter the size of the circle, what would be the best choice of circle for looking for studying more deeply the radian angle measures? And if you've thought about it for a second, I encourage you to do so. If you realize if we had a radius length of 1, okay, you had a radius length of 1, and something beautiful happens, right? If you have a radius length of 1, what is the arc length of 1 radian? Well, this distance is now going to be 1, right? So when I have a radius of 1, every 1 radian, right, is 1, right? And what it really does is simplifies the math for us, right? If, all of a sudden, we had, a radius of 8, well then 1 radian or 1 radius length would be, 8. And that would, it would be fine, but it wouldn't be as easy to work with as what's called a unit circle, where the radius is 1. And so this is going to allow us to look at radians more deeply and more simply. And so you'll get very familiar with the unit circle as this goes on, because a unit circle is going to be the basis for the function that we travel, that allows us to find the values of the x and y coordinates as we travel around a circle. So let's go ahead and take a look at that. Right, so here is a unit circle, and the unit circle is going to be what we use to think about angle measures in radians, because remember, we talked about this previously, it doesn't matter the size circle you use, the number of radians that it takes, or radius lengths, to go around a circle is going to be the same. And so when we use the unit circle, everything becomes a lot more simple, because now your radius has a distance of 1. And when you have a radius length of 1, that means that to travel 1 radian means that you've gone 1 unit around your unit circle. And this makes things a lot easier now. So now to think about it, the angle measure of an angle is simply just the length or distance of the arc that you've traveled around your unit circle, right? Because 1 radian would be 1 unit, 2 radians, 2 units, 3 radians would be 3 units on this arc, right? Because the radius length is 1. And so what we can do is we can think of the radian measure of an angle as the length of the arc around a unit circle. And this should make sense because, right, if we have an angle measure of 1 radian, right, that's when I have turned 1 radius length around this circle. 1 radius length has a length of 1. Right? And so we can use the unit circle to describe radians with much ease, because now with a unit circle, the angle measure in radians is simply the distance that I've traveled around the unit circle, because the radius length is 1. And so 1 radian will be an arc distance of 1 unit, 2 radians would be 2 units, 3 radians would be 3 units, 4 radians, right, would be 4 units, so on and so forth. And what we found is that to go all the way around a circle, right, and that's how we, our convention for defining an angle, right? Here's where it starts, and then I follow this around, and here's where it will end. A full turn, right? A full 360 degrees is going to be 2 pi radians, okay? So if, for example, if I said, okay, this angle here, that would be an angle measure, and what we're going to do is we're going to start using the variable theta. Okay, and theta, I'll draw it nice and big for you here. Theta looks like that. It's a Greek letter. And so this yellow angle here, we might say that is equal to 1 radian. Okay. And this purple theta here, this angle that goes all the way around, that is 2 pi radians. Remember, because how many radius lengths does it take to go all the way around the circle? Well, it takes 2 pi times r to get the circumference of a circle. So in this case, r is 1, right? So to go all the way around the circle will take exactly 2 pi units to go all the way around. And so my angle in radians of a full turn is going to be 2 pi radians. Okay? And the way we abbreviate radians is RAD. Okay? And remember, we use pi here, but the reason we use pi and not 3.14 is because pi is a number that goes on forever and ever. And so to be precise, we use the value of pi here written as the symbol pi, instead of saying that the radian measure of a full turn around the circle is 6.28. We'll use 2 pi. It's very close to 6.28, but we want to be as precise as possible. Okay, so this allows us to compute the value in radians for any angle that we currently know in degrees. And the reason that is that 2 pi radians is what degree turn? 360 degrees. Right? So let's say I wanted to know in radians, let's say I wanted to know, and this is going to be very key, so this is going to be a huge key to understanding radians in terms of what we currently know, which is degrees. And so let's say that I wanted to know the number of radians in 180 degrees. Well, if I want 180 degrees, I need to divide by 2, and since this equation is such, I have to divide by 2 on both sides. So if I divide by 2 on both sides, on the right side, I'm going to get what I'm looking for, which is 180 degrees. And on the left side, if I divide by 2, right, think about that, 2 pi divided by 2, I'll write it out here. 2 pi divided by 2, that 2 over 2 is 1 over 1, and so I'm left with pi. So pi radians is equal to 180 degrees, right? If I go halfway around the circle, how many radius lengths have I gone? Well, remember we checked it out. It was a little more than 3, right? And pi, obviously being a little more than 3, is 3.14, and so that is the arc length around a unit circle that takes me halfway around the circle, right? So 180 degree turn is a degree turn of pi radians. And so you can use this fact here to find the equivalent radian or degree measure for any radian or degree measure that you want. So I encourage you right now to pause the video and try it for yourself. So go to, say, pick any angle you want, and in degrees, because that's what we've been, that's what you've learned your whole life, and think about how could you find the equivalent radian measure, doing the same thing that we just did here. All right, so now I'm going to give you some simple, pretty simple questions that ask you to think about radians and degrees and convert between the two of them. So here we go. So here we're going to convert some angles to radians. So here you have some degree angles, and you're going to convert them to radians. And what I encourage you to do is, if you at first you're like, how do I do this? Just go back to that last slide and remember this fact, right? 2 pi radians is equivalent to 360 degrees. And using this, you can find the value of any degree measure, right? So what would you have to do to 360 to get 30, for example? Well, I'm sure you can figure that out. And since this is an equation, right, you're doing it to both sides, and that will tell you the equivalent radian measure. And then you can do the same thing here to convert each angle to degrees. So go ahead and go through these. Do these yourself. You can do them, I promise you. Just go back if you need to and rewatch how we found out the degree measure for 180 degrees using this simple equation. And I'll do one of these with you in just a second. All right. So hopefully these all went well. Nothing too crazy here. It should have been straightforward once you got the hang of it. To convert an angle to degrees, if I have it in radians, so imagine here that I wanted to find the angle pi radians in degrees. Well, I know that 2 pi radians is 360 degrees. So if I want just pi radians, I need to divide both sides by 2 to get pi radians. And when I do that, I find that pi radians, if I divide by 2 on the left, I'm left with pi. And if I divide by 2 on the right, I get 180. So pi radians is equal to 180 degrees. All right, so go through and make sure you've converted all of these angles either from radians to degrees. This is something that you're going to want to be very familiar with as we move forward. And then these questions over here on the right ask you to think about some kind of more real-world applications of radians and how you can use them to describe the angles that we turn around a unit circle. And just don't forget the key goal that we had, which was to find a function that could tell us the x and y coordinate of any point along a circle. And what we decided is that, we can think about any circle in the same way. All circles have the same angle measures as we go around them. And so looking at the unit circle makes it very, very simple. And what we're going to be able to do now going forward is to find a way to create a function that will tell us the x and y coordinate of any point around the unit circle. And we've just discovered the way of asking or telling us where those points are, right? So if I say, where's the point after rotating pi radians around a circle? Well, pi radians is, 180 degree turn, and so that point would be the point that is exactly halfway around the circle. And this will allow us to find exactly what those x and y coordinates are. So go ahead and finish up. Do 3 and 4. That's what I'll be looking for. Make sure you write the question down and give it some thought. For this last one here, I encourage you, it's a good idea to draw out an accurate representation of what it's talking about, and that will allow you to more clearly see the number of radians that has been rotated. All right, see you guys tomorrow.